So this is a formula that would, for a volume charge density, right? You could figure out the energy in a charge distribution by saying W is equal to 1/2 integral of rho v d tau. If you know the potential and the charge distribution, right, you could actually figure out the energy. Now, if you have a linear charge density or surface charge density, you could just replace, if needed, you can always replace rho d tau with sigma dA or with lambda dL. That's how these three always correspond with each other. Okay, so in this case we have a uniformly charged solid sphere of radius r. This is 232. And in part A, we're gonna use this equation to figure out how much work is in a solid sphere of charge of radius r solid and charge q. Right? So there's q on the sphere. Charge q and the radius is r.
Okay, but it's going to be fixed in 30 minutes?
Big R.
Okay, I appreciate that. That's all I want to do. Thank you.
We do have to find the potential. So there's two ways you could do that. You could either figure out the potential by using direct integration, similar to a problem we did before, taking infinity as your reference point because v at infinity is 0. That's one way to do it. I think the easier way in this case, due to symmetry, would be, because direct integration is going to generate an integral that's not so straightforward. The easier way would be, because of symmetry, we could use Gauss's law to find the electric field, and once we have electric field, we can just integrate the electric field to find the potential.
Right.
Probably be an easier way using that in this case.
Yeah.
And then once we have that, then it becomes somewhat straightforward to jump to the next step. I'll do it alongside with you here. Let's see. Gauss's law. So let's go for R greater than R outside. And so I would consider a Gaussian surface with this and with a radius r. So EDA equals Q enclosed over epsilon. In this case, I will enclose the entire Q. So this will be E times A because they're both in the radial direction. This is dA vector and this is E. Due to symmetry, I can pull E outside the integral. The angle is 0, cosine 0 is 1, so this just becomes E times A, which is 4 pi r squared of the Gaussian surface. I'm enclosing entire Q over epsilon, so the electric field will be Q, and this is in the radial direction, will be Q over 4 pi r squared epsilon, or let me write it in a more suggestive way. Q over 4 pi epsilon r squared in the r. This is in the radial direction. And now so this is for outside. Let's go inside. So inside the sphere, that's r less than r. So I will take a Gaussian surface inside the sphere here with the radius r. So E dA equals Q enclosed over epsilon. So in this case, I will not enclose the entire charge. Let's see how much we're going to enclose. So Q enclosed is equal to rho d tau on V. How much is rho? Well, we have Q divided by 4/3 pi r cube, and this is all a constant. Integrate on d tau, and d tau is just the volume of the sphere, so this becomes Q over 4/3 pi r cube, and you know, d tau on V, the volume of the Gaussian surface, the green surface, is just 4/3 pi r cube, and I could cross these with these, and I would get Q enclosed to equal Q r cube over r cube. And now back to Gauss's law, I will get E times 4 pi r squared equals Q r cube over epsilon r cube. Can cancel r squared with r squared, and I will get E to be Q over 4 pi epsilon r cube multiplied by r, and this is also in the radial direction. Okay, now that I have my electric field, I could find my potential. So now let's go find V. So let's go for R greater than R first. I know that V R is equal to the integral of E dr. This pad doesn't like me. Keeps on closing here. Okay, so let's go. R is greater than R, so V is equal E dr from infinity to all the way to R. So outside, the electric field was Q over 4 pi epsilon In fact, wait a second, I don't really need this. I just need inside the sphere for the purposes of this question. So let's do it for r less than r. So this is from minus infinity to r. Right, so the outs plus minus, there's a minus sign here, and minus r to r going inside the sphere. So this is E outside, and this here will be E inside dot dr. Okay, so V will be minus infinity to r. So E outside turned out to be Q over 4 pi epsilon r squared dr minus r to r. E inside turned out to be Q over 4 pi epsilon r cubed. This is all a constant. I can take the integral here. R dr from r to r, and here this is Q over 4 pi epsilon is all a constant. So Q over 4 pi epsilon. Making sense, Ben?
Yeah.
Dr. So you have to find the potential.
Right.
Dr over r squared. From infinity to r. Okay, so we will get.
We do this like the one with the disk, except for the sphere.
The
triple integral version.
It's a bit tougher to do it that way with the integration. I would suggest finding the electric field using Gauss's law, the way I'm doing it, and then from the electric field you can integrate the electric field to find V.
Okay.
You could do it that way. It's doable, but it's just much more complicated. So this is minus Q 4 pi epsilon. This is minus 1 over r from infinity to r minus Q over 4 pi epsilon r cubed r squared over 2 from r, big R to small r. Let's evaluate. The first one, of course, vanishes at infinity, so we get plus 1 over r, and the second term is 0. Here we have minus Q over 4 pi epsilon r cubed. We get r squared over 2 minus r squared over 2. And let's see here, if we simplify this guy, what do we get? Let's go with this inside. 4 pi epsilon 1 over r minus Q over 4 pi epsilon r cubed times r squared over 2 plus Q over 4 pi epsilon 1 over 2r. And here we have 1 over r, so we can multiply this by 2 and this by 2, and if we add them we get 3. So then V becomes 3 Q over 4 pi epsilon 2r and then we have minus q over 4 pi epsilon r cube, or let's write it in a bit of more suggestive way, r squared over 2r cube. And if we factor out q over 4 pi epsilon and 1 over 2r, from the first one we have left 3, and from the second one we have left r squared over r squared. Okay, so this is our potential. And now that we have the potential inside, we can go back and plug it in the work formula. So we will get work is equal to 1/2 integral of rho v, this entire thing. Let me pull the constants out. So q over 4 pi epsilon 1 over 2r rho v 3 minus r squared over r squared d tau on v. Okay, now this guy is nothing but charge over volume. So this will be 1/2 q and 4 pi epsilon. This is constant uniform charge density, so I'm gonna pull this out here, and this is just q over 4/3 pi r cube, and we have here 3 minus r squared over r squared times r squared sine theta dr d theta d phi, and we have a triple integral with r going from 0 to r to encompass the entire sphere. Theta is going from 0 to pi, and phi is 2 pi, and 0 to pi for phi. Sorry, to 0 to 2 pi for phi, and 0 to pi for theta. Okay, so let's see what all that gets us. So let's evaluate this. So we have q squared over we have here, let's put these together. We have 16 times, we have a 3 here, and here we have 16 times 4. 16 times 4, we have a pi squared, and we have epsilon, and we have r4. The d phi term will get us a 2 pi, and the sine theta will get us a 2, so that's a 4 pi, and the rest is 0 to r 3 r squared minus 1 over r squared r4 dr. Okay, let's do this. So 2, 2, 4, 4, pi with pi. We have left 3q squared over 16 pi epsilon r4, and this integral comes out to be r cubed minus 1 over r squared, r5 over 5 from 0 to r. The 0 will kill it, and then the capital R will make this 3q squared 16 pi epsilon r4. We have r3 minus r5 over r squared will be r cubed over 5, and so this simplifies to 4/5. So this becomes 3q squared 16 pi epsilon r4 4/5 r cubed. And finally we can simplify this down to 1 over 4 pi epsilon. We have 3/5 q squared over r. This is the work or the energy stored in this uniformly charged solid sphere.